Hello everybody. In the last lecture, I discussed about a homogeneous function and some results containing first order partial derivative and second order partial derivative of a homogeneous function. In this lecture, we shall discuss about a tangent plane and normal line of a surface, then linear approximation, and finally expansion of a function by using Taylor's theorem for function of two variables. Let us start from the tangent plane to a surface. We know that f of x, y, z is equal to c represents a surface in the three-dimensional space. The tangent plane to the surface f of x, y, z is equal to c at the point P x0, y0, z0 is given as x minus x0 into del f by del x at the point x0, y0, z0 plus y minus y0 into del f by del y at the point x0, y0, z0 plus z minus z0 into del f by del y at the point x0, y0, z0 is equal to 0. Now we come to the equation of a normal line to the surface. We have this f of x, y, z is equal to c be a surface in the three-dimensional space, and the normal line to the surface of f of x, y, z is equal to c at the point P x0, y0, z0 is given as x minus x0 upon del f by del x at the point x0, y0, z0 is equal to y minus y0 upon del f by del y at x0, y0, z0 is equal to z minus z0 upon del f by del z. This is del f by del z instead of del f by del y at the point x0, y0, z0. Now let us take some example to find the tangent plane and normal line for given surfaces or given function. Let us take first example. Find the equation of a tangent plane and normal line to the surface x, y, z is equal to 6 at the point 1, 2, 3. Clearly, this is representing the surface x, y, z is equal to c. We can write this x, y, z is equal to 6 in the form of f of x, y, z is minus 6 is equal to 0, or we can take f of x, y, z is equal to x into y into z minus 6. Now differentiating the given function with respect to x. So fx at the point x, y, z is yz because yz is constant and partial differentiation of x with respect to x is 1. So this is del f by del x is yz at the point x, y, z. But we require to find the partial derivative of the function at the given point, and given point is 1, 2, 3. So fx at the point 1, 2, 3 is this 2 into 3, so 6. Similarly, we can find the partial derivative of f with respect to y at the point x, y, z as xz because partial differentiation of x, y, z with respect to y is xz, and finding the same partial derivative of f with respect to y at the given point 1, 2, 3 which is equal to 1, x is 1 and z is 3, so 1 into 3 is 3. And finally the remaining third partial derivative of the function f at the point z is xy, because partial derivative of z with respect to z is 1 and xy is constant with the variable, so it remains as it is, and derivative of 6 is 0. So f suffix z at the point 1, 2, 3 is equal to 2, because x is 1 and y is 2 because of this point. Now we know that the equation of the tangent plane at the point P at P or 1, 2, 3 is x minus x0 into del f by del x at the point 1, 2, 3 minus y0, sorry, it is plus y minus y0 into del f by del y at the point 1, 2, 3 and plus z minus z0 del f by del z at the point 1, 2, 3 is equal to 0. So x0, y0 and z0 are the values 1, 2 and 3. So we are substituting the values of x0, y0 and z0 respectively as 1, 2 and 3. So x minus 1, y minus 2 and z minus 3. Now substituting the value of del f by del x. So at the point 1, 2, 3 is 6. So this is 6. Similarly del f by del y at the point 1, 2, 3 is 3, and this del f by del z at the point 1, 2, 3 is 2. So our equation becomes x minus 1 into 6 plus y minus 2 into 3 plus z minus 3 into 2 is equal to 0. Simplifying this, so 6x minus 6 plus 3y minus 6 plus 2z minus 6 is equal to 0. This minus 6 minus 6 minus 6 becomes minus 18, and it is taken on the right hand side, so it will be plus 18 on the right hand side, and the remaining on the left side is 6x plus 3y plus 2z. So finally the equation of the tangent plane is 6x plus 3y plus 2z is equal to 18. Now for the normal line we have to take this as ratio instead of multiplication. X minus x0 upon del f by del x, y minus y0 upon del f by del y, and z minus z0 upon del f by del z. And instead of this plus sign we shall have equal to sign, not this equal to sign. Okay, now our equation is, as I told you, x minus x0 upon del f by del x at the point P or x0, y0, z0, which is equal to y minus y0 upon del f by del y at the point x0, y0, z0 is equal to z minus z0 upon del f by del z at the point x0, y0, z0. So the value of x0 is 1, y0 is 2 and z0 is 3. So x minus 1, we have already calculated all these partial derivative at the given point 1, 2, 3 are 6, 3 and 2 respectively. See, 6, 3 and 2. So our equation of a normal line at the point P is x minus 1 upon 6 is equal to y minus 2 upon 3 is equal to z minus 3 upon 2. So this is our final equation of a normal line. Now let us take another example. Find the equation of a tangent plane and normal line for the ellipsoid, which is given by x square by 4 plus y square plus z square by 9 is equal to 3 at this point minus 2 comma 1 comma minus 3. So we start from this equation, and it can be written in form of f of x y z comma c is equal to 0. So our f of x y z is equal to x square by 4 y square plus z square by 9 minus 3. Now we have to find the partial derivative at this given point. So first we find partial derivative of f with respect to x, with respect to y, and with respect to the z. And after finding all the partial derivatives, first order partial derivatives, we substitute the x is equal to minus 2, y is equal to 1, and z is equal to minus 3. So it is very easy to calculate partial derivative of f with respect to x is 2x by 4, and after simplification it will be x by 2, and derivatives of y square and z square and 3 is again 0. So we find partial derivative of f with respect to y at this point x, y, z is 2y, so this is 2y, and fz partial derivative of f with respect to z at this point x comma y comma z is equal to 2z by 9. So we calculate this partial derivative at this point minus 2, 1 and minus 3. So del f by del x at the point minus 2, 1, minus 3 will be minus 2 by 2, so minus 1. Similarly, del f by del y at the point minus 2, 1, minus 3 is equal to 2 into this 1. Y is 1, so 2 into 1 is 2. Now fz at the point minus 2, 1, minus 3, so 2z by 9 and z is equal to minus 3. So we get the value minus 2 by 3. Hence the equation of the tangent plane at the point 2, minus 2, 1, minus 3 is x plus 2 into minus 1. This is the partial derivative of f at the given point. So this is minus 1. We can write directly that x minus x0 into del f by del x at the point x0, y0, z0 plus y minus y0 into del f by del y at the point x0, y0, z0 plus z minus z0 into del f by del z at the point x0, y0, z0 is equal to 0. So x0 is equal to minus 2, y0 is equal to 1 and z0 is equal to minus 3. So we get x plus 2 into the partial derivative at given point, so it is minus 1 plus y minus 1, y minus 1 into this partial derivative at minus 2, 1, minus 3 is equal to 2, and this z plus 3 into minus 2 by 3, which is equal to 0. So after simplification we can write down, here we are taking 3 as LCM, so minus 3, 6, and 2 will be, minus 2 will be there, and the denominator 3 will be gone out on right side, so it will become 0. So our equation is x plus 2 into minus 3 plus y minus 1 into 6 plus z plus 3 into minus 2 is equal to 0. So we get this minus 3x into minus 3x in minus 6, then 6y minus 6, and then minus 2z minus 6. So after simplification we get minus 6, minus 6, minus 6 becomes 18, minus 18, and it is taken on the right hand side, and this side it is minus 3x, so both sides we are changing the sign, so minus 3x becomes plus 3x, then this 6y becomes minus 6y, and minus 2z becomes plus 2z, and this is minus 18, plus 18 becomes minus 18. So this is final equation of the tangent plane for the ellipsoid x square by 4 plus y square plus z square by 9 is equal to 3 at this point minus 2, 1, minus 3. Now for the normal line to this surface at this point is taken as x by 2 into minus 1 is equal to y minus 1 by 2 is equal to z plus 3 upon minus 2 by 3. So we write down it and I show you on the board. So x plus 2 upon minus 1, y minus 2 upon 2, and z minus 3 upon minus 2 by 3. We can simplify this further if we require. Now we come to the next topic of linear approximation. If z is equal to f of x y z is a differentiable function at the point p x0, y0, then the tangent plane to the surface z is equal to f of x y remains very close to the surface near to the point x0, y0. So the surface can be assumed to behave like a tangent plane near the point, and tangent plane can be used as an approximation of the surface, and this approximation is known as linear approximation of the function or surface. So suppose we have the tangent plane z is equal to f of xy, then this equation can be written in the form of f of xy minus z is equal to 0, and the tangent plane for this f of x comma y minus z is equal to 0 can be given as x minus x0 into fx at the point x0, y0, z0 plus y minus y0 into fy at x0, y0, z0 plus z minus z0 into del f by del z at the given point, but we know that del f by del z for this will be minus 1. So that's why this minus 1 is written. One step is skipped for this, and this minus 1 is substituted for del f by del z from this equation f of x comma y minus z is equal to 0. Solving this equation for z, so this minus z is there and it is taken on the right hand side, so we get z is equal to this minus z0 and minus 1 becomes plus z0, z0 x plus x minus x0, and this is the remaining point, so x minus x0 fx at x0, y0 plus y minus y0 fy at x0, y0. After this we know that z0 is the point f of x0, y0, so we substitute this value, and z is nothing but f of xy, so we are substituting the value for z and z0 as f of xy and f of x0, y0 respectively. So our equation becomes f of xy is equal to f of x0 plus x minus x0 fx at x0, y0 plus y minus y0 fy x0, y0. Near to the point x0, y0, the surface behaves like the tangent plane and it is very close to tangent plane. Thus we can approximate the surface as a tangent plane at that point as f of xy is approximately equal to f of x0, y0 plus x minus x0 fx at x0, y0 plus y minus y0 into fy at x0, y0, and this is called linear approximation of the function z is equal to f of xy near the point x0, y0. Now let us find the linear approximation for some function. So let us take one example. Find the linearization. Another name is linearization for the linear approximation. So we write find the linearization of the function f of xy is equal to x into e raised to xy at the point 1, 0 and use it to approximate this value 1.1, minus 0.1. Clearly, our function is f of xy is equal to x into e to the power xy. Now, we know the linear approximation for the function f of xy is denoted as L of xy, and it is same as f of xy into x minus x0 into fx at xy and y minus y0 into fx at fy at xy. So we find this derivatives, partial derivative in fact. Okay, so fx, okay, let me show you the formula on the board so that you can clearly understand. Yeah, this is the formula for the linear approximation. This is approximate and we can denote it as L of xy. So L of xy equal to f of x0 y0 plus x minus x0 into fx at x0 y0 plus y minus y0 at this point. Now we take fxy is equal to x into e to the power xy. Now for the partial derivative we have to differentiate partially with respect to x. So u into v rule can be applied because x is in two places and multiplication is present in between those two places. So x is as it is, and partial derivative of e raised to xy is equal to e raised to xy into y, and partial derivative of x is 1 and e raised to xy is as it is. Now we substitute 0 point for the function. So f at the point 1 comma 0 is 1 into e to the power 1, so 1 fx at 1 0, so 1 comma 0 e to the power 0, e to the power 0 is 1. So ultimately this value, partial derivative of f function at the point 1 0 with respect to x is 1. Similarly we can find the partial derivative of f with respect to y is x square e raised to xy. From here x is constant and partial derivative of e raised to xy is e raised to xy into x. So x, new x will be multiplied, so x square into e raised to xy. Now we find the partial derivative of f with respect to y at point 1. So fy at 1 0 is 1 square into e raised to 0, so 1. Hence the linearization of the function is 1 minus 0 f of x0 y0, so 1 f of 1 0, so 1, so x minus x0, so x minus 1, and the value of fx at this point is 1, so x minus x0, so x minus x0 is 1, x minus 1, and this is the value of the partial derivative, this one fx, plus 1 into y minus y0, so y0 is 0, this one 0, so y minus 0 is y, and this is the value 1 for the partial derivative of f with respect to y at this point 1 0. Using this linearization to approximate 1.1 comma 0.1, so we can find the value of f of 1.1 at minus 1 is given as this. (1.1 minus 0.1), so ultimately we get the value 1. Fine. Now let us take another example. Find the linear approximation of the function f of xyz is equal to x square minus xy plus 3 sin z at the point 2, 1, 0. Clearly, f of xyz is the given function x square minus xy plus 3 sin z. Now we find the value of this function at this point 2, 1, 0 by substituting 2, 1 and 0 for x, y and z respectively. So f of 2, 1, 0. So 2 square minus 2 into 1 plus sin 0 is 0. So we get 4 minus 2 plus 0, so 2. Similarly, we can find the partial value of the partial derivatives with respect to x, y and z at the given point. For that, we are differentiating given function partially with respect to x first. So del f by del x at the point x, y, z is 2x minus y, and derivative of this is 0. So we get 2x minus y, and substituting the value for 2, 1 and 0 for x, y, z. So partial derivative fx at the point 2, 1, 0 is 2 into 2 minus 1 into minus 1. So 2 to the 4 minus 1 is 3. Now partial derivative f with respect to y, partial derivative of f with respect to y is minus x, because this is 0, this is 0, because we are differentiating with respect to y, so remaining variable are treated as constant. So this is constant 0, this is constant, it becomes 0 after partial differentiation. This remains as it is because it is with variable, so derivative of y is 1 and minus x remains as it is. So we get this minus x, and we find the partial derivative of f at 2, 1, 0 with respect to y is minus 2. So similarly, we can find the partial derivative of f with respect to z is this is 0, this is 0, and partial derivative of sine z is cos z into 3 remains as it is, so 3 cos z. Now we have to substitute 2, 1 and 0 for x, y and z respectively. So fz at 2, 1, 0 is 3 cos 0 is 3. Hence the linear approximation of the function f of x, y, z is L of x, y, z, which is equal to 2, this 2, f of x 0, y 0, z 0, plus 3 into this 3 is for the partial derivative with respect to x at the given point. So del f by del x at 2, 1 into x minus x0 is 2, plus del f by del y into y minus y0. Value of del f by del y is equal to this minus 2, and y minus y0 is y minus 1 because y0 is 1, plus del f by del z into z minus z0, but the value of del f by del z at the given point is 3, and z minus z0 is z minus 0. So we simplify this and we get 2 plus 3x minus 6 minus 2y plus 2 plus 3z, and this becomes 3x minus 2y plus 3z minus 2. So this is another example to find the linearization of the given function. Now we want to discuss Taylor's theorem. So Taylor's theorem for function of two variable can be given as f of x plus h comma y plus k is equal to f of x comma y plus h into del by del x plus k into del by del y. This is y. This is y. Into f of x y plus 1 upon 2 factorial h into del by del x plus k into del by del y. This is again y. Whole square for the function f of x y, and so on. We can find the higher order partial derivative using this form, provided z is equal to f of xy is a differentiable function at xy point this can be written in form of f of x plus h comma y plus k is equal to f of x comma y plus h into partial derivative of f with respect to x plus k into partial derivative of f with respect to y at the given point xy plus 1 upon 2 factorial into h square into fx square plus 2hk fxy plus k square fy square at the given point. This theorem is used to expand or approximate the given function z is equal to f of xy in the form of polynomial near the point x0, y0. So we can write f of x0 plus h, comma y0 plus k is equal to f of x0, comma y0 plus h into fx, partial derivative of f with respect to x, plus k into fy, partial derivative of f with respect to y at the given point x0, y0, and the remaining term can be written very easily. It is very much clear from this, right? We can write down 1 upon 2 factorial h square into fx square plus 2hk into fxy plus k square into fy square at the point x0, y0, and higher order derivative can be written. Okay, so by taking x plus h is equal to x0 and y plus k is equal to y0, we get another form for the Taylor's theorem. So in this we get x0 plus h as x and y0 plus k as y. So we get f of xy is equal to f of x0, y0 plus x minus x0 into partial derivative of f with respect to x at the point x0, y0 plus y minus y0 into partial derivative of f with respect to y at the same point x0, y0 plus 1 upon 2 factorial multiplied by this all terms, which are x minus x0 whole square into fx square plus x0, okay, plus 2 times x minus x0 into y minus y0 fxy at the point x0, y0 plus y minus y0 square fy square at x0, y0. So this is the another form for Taylor's theorem. This is also known as expansion of the given function f of xy in powers of x minus x0 and y minus y0, x minus x0 and y minus y0. Let us take some example to expand the given function by using Taylor's theorem. So first example, expand f of xy is equal to e to the power xy by using Taylor's series at the point 1, 1 up to the second degree terms. So here our function is f of x, y is equal to e to the power xy. Now we write the Taylor's theorem. So f of xy is equal to f of ab plus x minus a into fx at ab plus y minus b into fy at ab plus 1 upon 2 factorial into the bracket x minus a whole square into second order partial derivative of f with respect to x at ab plus 2 times x minus a into y minus b fx y at the point ab plus y minus b whole square into fyy at ab plus the remaining terms of third order partial derivative or third degree of x minus a and y minus b. Now we want to take a is equal to 1 and b is equal to 1. A is equal to 1, b is equal to 1. So we have to find this f11. For that we substitute x is equal to 1, y is equal to 1. So f of xy is equal to e to the power xy. f11 is equal to e fx at xy, which is equal to y into e to the power xy, which is f. Now we substitute x is equal to 1 and y is equal to 1 in the partial derivative of f with respect to x. So we again get this 1, e to the power 1 into 1, so e. Then we find the partial derivative of f with respect to y as e to the power xy into x, because we have to assume this as the variable. So e to the variable, derivative of e to the variable is e to the power that into derivative of xy with respect to y is x. So we get this. Now we calculate the partial derivative with respect to y at point 1, 1 is equal to e. Now f xx, which is second order partial derivative with respect to x only, so it is obtained by differentiating first order partial derivative with respect to x again. So y is constant, so we keep it as it is, and partial derivative of e raised to xy with respect to xy is e raised to xy into y, so y into y, so y square e raised to xy. Now fxx is equal to 1, fxx at the point 1, 1 is equal to e. Now we find partial derivative of f with respect to y first and then x. So it is calculated as xy e raised to xy, very clear from this. See, we have this fy and we are differentiating it with respect to x. So it is, it is this one, xy into, so f of xy at the point 1, 1 is equal to e. So fy y at xy point is x square e raised to xy, so fyy at 1, 1 is e again. Substituting these values in equation which is Taylor's theorem, equation 1 is Taylor's theorem, so we are substituting that values. So we get f of xy is equal to e into x minus 1 into e plus y minus 1 into e plus 1 upon 2 factorial into x minus 1 whole square into e plus 2 times x minus 1 y minus 1 into e plus y minus 1 whole square into e, and so on. So e is present in each and every term, so e can be taken as common factor. So e into the bracket 1 plus x minus 1 plus y minus 1, x minus 1 whole square plus 2 into x minus 1 y minus 1 plus y minus 1 square plus the remaining term by 2 is also there. Okay, because of 1 upon 2 factorial, so we have to write down this 2. So this is the expansion of function e to the power xy at the point 1, 1. Now we take another example. Expand e to the power x into cos y in powers of x and y as far as the term of the third degree is concerned. Let us take f of xy as e to the power x cos y. By Taylor's expansion, f of xy is equal to f of 0, 0 plus x into fx at the point 0, 0 plus y into fy at the point 0, 0 plus 1 upon 2 factorial into the bracket x square into fxx at 0, 0 plus 2xy into fxy at 0, 0 plus y square into fy y at 0 0 plus 1 upon 3 factorial. These terms are necessary because in the question it is mentioned that we have to expand this function up to the third degree terms. So that's why we are writing. So x cube fxx x. So this is partial derivative of f with respect to x 3 times. This is 3x square y into 2 times partial derivative with respect to x and 1 time partial derivative with respect to y. So fxxy and plus 3xy square into fxyy at 0 0 plus y cube into fyy at point 0 and so on. This is denoted as equation number 1. Now we need to find the values of first order, second order and third order partial derivative at the 0 point. So first we find fxy at 0 0. So e raised to 0 is 1, cos y cos 0 is 1. So f0 0 is 1. Now we find the partial derivative of f function with respect to x. So derivative of e raised to x is e raised to x, cos y is constant, so cos y, and fx at 0 0 is 1. Now we find partial derivative of f with respect to y at point xy. So e raised to x is as it is and derivative of cos y is minus sin y. And we find this value of partial derivative at 0 0 point. So because of this sin 0 is 0. So 0 into 0, 0 into this is 0. So fx x second order partial derivative of the function at xxx is e raised to x into cos y. fxx at 0 0 is 1. Similarly, we can find fxy. So first we are differentiating function with respect to y and then x. So this is e raised to x into sin y, and with respect to x, so e raised to x again. So we are getting minus e raised to x sin y, and substituting xy as 0 0, so 0 0. So fxy at 0 0 is 0. fyy at point x comma y is equal to e raised to x cos y. fyy at 0 0 is equal to minus 1. And similarly we can find out the third order partial derivative with respect to x. So fxx x at xy, so 3 times derivative of e raised to x is e raised to x only, so e raised to x. Cos y is constant because it does not contain any variable x. Okay, so this cos y as it is. fxx at 0 0 is e raised to 0 1, and cos y cos 0 is 1, so this value is 1. Now fxxy, so 2 times partial derivative of e raised to x is e raised to x, and 1 time partial derivative of cos y is minus sin y. So this, due to this minus sin y, this minus is written, so e raised to x into minus sin y. fxxy at 0 0 is 0. Now fxy y, so 1 time derivative of e raised to x with respect to x, and 2 time derivative of cos y with respect to y. So we get cos y as minus sin y and again cos y. So ultimately we get e raised to x into cos y, this, and this value at point 0 0 fxyy at 0 0 is minus 1. So fyy y at the point xy, so 3 times partial derivative of f function with respect to y. So e raised to x is constant because it does not contain any y, and derivative of cos y is minus sin y, then minus cos y, and then again minus sin y. So minus and the previous minus sign becomes plus sign, so e raised to x sin y. So this is there. So fyy y at the point 0 0 is 0. Now we substitute these values in this result. So f of xy is e raised to x into cos y. So this is cos, and this value is 1. We can see that this. So ultimately we get e raised to x cos y as 1. Then x into partial derivative of f with respect to x at 0, 0 is 1. See this fx at 0, 0, 1. Then y fy at 0, 0, so it is okay, this, it is 0, this is 0, and then plus 1 upon 2 factorial x square into fxx at 0, 0 is 1, plus 2xy into fxy at 0, 0 is 0, plus y square into fy square is minus 1. Let me show you. Fy square, yy or fy square, where is it? This. So it is minus 1, right? Fine. Then third order partial derivative multiplied by 1 upon 3 factorial and the remaining terms. So x cube into fxx x 3 times partial derivative of f with respect to x is 1. fxxx 3 times x, so 1. Then fxxy is 0 and fxyy is minus 1. 1 0 minus 1 0 we have to remember and substitute those values. So let me show. Okay, yeah, this 1 0 minus 1 0. So x cube into third order partial derivative of f with respect to x, 2 times third order partial derivative of f with respect to 2 times x and 1 time y. So this value is 0 and similar for this. So we get e to the power x cos y is equal to 1 plus x plus 1 upon 2 factorial is 2, x square minus y square, this x square, this is 0, so x square minus y square, plus 1 upon 3 factorial is 1 by 6. This is x cube plus this is 0, this is minus 3xy square, this plus 0. So this is the expansion of e raised to x cos y near the point 0, 0. Right? Fine. Now let us take one more example. Expand f of xy is equal to sin x cos y in powers of x minus pi by 4 and y minus pi by 4. By Taylor's theorem, we know that f of xy is equal to f of x0 y0 plus x minus x0 into del f by del x at x0 y0 plus y minus y0 fy at x0 y0 plus 1 upon 2 factorial x minus x0 whole square into fx square at x0 y0 plus 2 times x minus x0 into y minus y0 fxy at x0 y0 plus y minus y0 square fy square at x0 y0 plus 1 upon 3 factorial this terms, right? So now we want to expand, or we want to expand the given function near the point pi by 4, or we require to expand the function in powers of x minus pi by 4, y minus pi by 4. So taking x0 y0 is equal to pi by 4. So we can find out the value of the function at pi by 4 comma pi by 4 and their partial derivative, first order partial derivative and second order partial derivative, and substitute those values here. So we get this. So f of xy is sin xy cos y, f pi by 4 is 1 by 2, fx at xy cos xy cos y. This way we are calculating these values. Okay, you can easily calculate these values yourself and substitute those values in the Taylor's theorem. So we get this, and ultimately here today we have discussed about the tangent plane and normal line for the surface. Then we learn how to find the linear approximation of a function, and then how to expand the given function of two variables by using Taylor's theorem. Thank you.